Hello everyone. Today we will be discussing Chapter 10, Modeling and Analysis. I'm Brittany.
Kim.
Chris. And Tobias.
The chapter had a lot of great information, so we just decided to pick out a few topics that we thought were important. The first thing we'll be discussing is search methods, simulation, visual simulation, genetic algorithm, and evolver. First, I'm going to discuss what a search approach is. It's a general method or category of closely related methods used to find the best solution to a problem based on some sort of criteria. There's three main search types: optimization, blind search, and heuristics. Optimization is more geared toward structured problems, which are easy, most often mathematical problems. And the next part of optimization is you get the best solution directly, and it stops when there's no improvement possible. Blind search is more for unstructured problems, the more complex problems for management. And there's two types of blind searches. There's complete enumeration, which all alternatives are considered, and the optimal solution is discovered. The next type of blind search is partial search, which it continues until a good enough solution is found. So this search type can take a very long time. So you would need a lot of resources and a lot of time to use that particular search method. Last but not least is heuristics. For this search method, rules are required, and they help guide the search process and reduce the number of necessary computations. And this is feasible for complex problems, and only promising solutions are considered.
Next, we're going to talk about simulation, which is defined as the appearance of reality. You would often see or conceive a simulation as a computer graphical model, but it also could be a manual simulation, which is like a physical model. And it's a real-life situation, so it, in fact, imitates reality. Simulations are used as a technique to conduct what-if analysis, test out different scenarios without doing it in real life in order to find out the best solution. Often used for conducting experiments, it's often used with complicated DSS or decision support systems when other techniques cannot solve a problem due to complexity. Because reality really is complex and involves some randomness, so mathematics can't always solve or create an optimal solution. One of the cases that you read in the book was a scenario about a hepatitis B outbreak, and they used simulation in order to try to reduce additional occurrences of the outbreak. It was used as an optimal methodology due to the length of time that it would have taken in order to perform clinical trials. So the result ultimately was able to provide them feedback in terms of making a combination of efforts to perform blood tests and vaccinating associates of the infected. The major characteristics of simulation are its ability to test values or uncontrollable variables in a model and observe the impact on output variables. It does use the descriptive methodology, and it's used only when problems are too complex to be treated using numerical optimization techniques. For instance, a problem may exhibit risk or too many interactions with variables or moving parts. Advantages and disadvantages. Some advantages are it's pretty a straightforward method. It does provide some time compression, such as what we had discussed earlier about the case about hepatitis B. It does allow you to experiment with alternatives and can be used for a wide variety of problem types. For disadvantages, it can't always guarantee an optimal solution. It could be slow and costly, problem-specific, and software might require special skills. Here's a visualization of simulation methodology, which looks fairly similar to our other charts for methods. So this one, you want to first define the problem, then construct your model, test and validate that model, design your experiments, conduct those experiments, evaluate your results, and then implement solutions. As for simulation types, these are the most important ones, which start with probabilistic or stochastic, which means one or more of the independent variables are probabilistic, which follow probability distributions, either discrete with limited variables or events, or continuous distribution with unlimited events. For time-dependent versus time-independent simulations, the main difference is that for dependent, it's not important to know exactly when an event occurred, versus independent, time is important, such as a wait time in a doctor's office or fast food line or something like that, in which a company might want to improve that wait time. Monte Carlo simulation is one that is most commonly used for business decision problems. This involves creating a model, then determining uncertain variables, and that is by researching past data in order to estimate your values. And then you run sampling experiments by selecting random values for variables and computing variables affected. And this can be done hundreds or even thousands of times. After that, you want to analyze your behavior of these variables by looking at their statistical distributions. There are many simulation programs that offer the ability to run this type of simulation because of the hundreds of thousands of times you have to run your sampling experiments. Final type is discrete event, which refers to building a model where interactions between different entities are studied. For example, fast food restaurant, which involves time a consumer arrives, waits, give your order, served the food ultimately. It's used to estimate performance of a system, wait times, length of the queue. Other applications include manufacturing, such as in the case that we're going to discuss later.
All right, so the next section is visual interactive simulation, which is also known as visual interactive modeling. This shows a decision maker a representation of the decision-making situation in action. This type of simulation also helps overcome some of the inadequacies of conventional methods. Some of those inadequacies include it lacks the ability to show the decision maker how a solution evolves over time. It also lacks the ability of the decision maker to actually interact with the simulation itself. And then if the simulation results do not match the intuition or judgment of the decision maker, it can also result in a confidence gap. So visual interactive modeling really lets the decision maker see what the model is doing and how it interacts with the decisions being made as they are being made. It helps with enhanced learning about both the problem and the impact of the alternative solutions that are being tested. It also uses a computer graphic display to present the impact of different managerial decisions, and has been used as a decision support system in several operation management decisions, such as wait line management, which the case 10.4, which we had asked the class to prepare, provides another example of this. And as a side note, there's hundreds of simulation packages that are available. One of these packages, Simio, which we'll show a brief demo on later on in the presentation. So the next section is system dynamic modeling. System dynamic models are macro-level simulation models which aggregate values and trends are considered. The main objective here is to study the overall behavior of a system over time rather than each individual behavior each individual participant in the system. Another major key dimension is the evolution of the various components of the system over time and a result of their interaction between the various components. System dynamics modeling is used extensively in the information technology area, and possible changes are projected and analyzed through conceptual models and simulations. So in essence, it really just allows the decision maker to analyze strategies and trade-offs that are hard to investigate. To create a system dynamic model, first you have to draw a causal loop diagram for all processes that lead to some benefit. This is a qualitative step where the processes, variables, and relationships are identified. Then you're going to take that information and transform it into mathematical equations that represent the relations among the various variables. These equations, and then the stock and flow diagrams, which is the causal loop, are then used to simulate practical and theoretical scenarios. As a set-aside on this one as well, the causal loop diagram shows the relationships between the variables in the system, and the feedback process is a key component of this diagram. What the causal loop tries to do is draws a link between the elements and depicts how one change in one element leads to a change in another element. This is depicted by a positive indicator, which shows that the change in one element moves in the same direction as the other, and if there's a negative, as a negative, when their change is in opposite directions. The next section is agent-based modeling. The text or the chapter starts off with giving the concept of agency, which pretty much the term agent is derived from the concept of agency, referring to employing someone to act on behalf of another. So in that essence, agent-based modeling is a simulation model technique to support complex decision systems where a system or network is modeled as a set of autonomous decision-making units that individually evaluate their situation and make decisions on the basis of a set of predefined behaviors or rules. It focuses on adaptive learning rather than on optimization. There was a framework that the chapter discussed on how to build an agent-based model. Those steps include the following. First, we're going to identify the specific problem to be solved, the agent and theory of agent behavior. Next, you're going to want to identify the agent relationships and the theory of the agent interaction. This can be done by studying the agent's environment. Then you're going to collect the required agent-related data. And the final step is the performance of the agent-based system should be validated. And this system should be used in situations where certain characteristics make a system difficult to understand or predict, such as a flock of bird migration, housing segregation, and urban issues, and certain operation management problems, as the chapter alluded to. This is going to conclude this portion of our presentation. The next video, we're going to talk about genetic algorithms.